Welcome back to Combo Class. Today, I want to tell you about a very underrated concept about numbers. One of the most underrated concepts in mathematics. In fact, maybe as a mathematician, I think it could be the most underrated concept in the branch known as number theory. This concept, known as integer complexity, does not relate to the type of complexity that many people would expect, like analyzing the complexity of certain computer algorithms. It's its own thing, integer complexity, that I bet a lot of you don't know. And I bet that for some reason, a lot of mathematicians don't know this concept, despite the fact that it's a simple enough concept that when I was younger, I stumbled on it myself. But since it's so underrated, I had to do all these personal investigations and then type a list of numbers into what's known as the online encyclopedia of integer sequences to even find this name, integer complexity. I often like to ask a question about numbers and go down a rabbit hole of exploring it and investigating it myself to see what I can find. And one question I asked was, how many ones is each number made out of? One is the unit, and additively is the building block of all the natural numbers. But if we were just using addition, this would be a super trivial question. Like 3 is made out of 3 ones added together. 7 is 7 ones added together. But what if we allowed other operations? When I added multiplication into the mix, the question became a lot less trivial. I tried to see how many ones it would take to make different numbers if I let myself add them or multiply them, and do that in whatever order I chose, basically letting myself also use any amount of parentheses I needed. And then some very interesting patterns and questions emerged. Now we're going to be looking for the minimum amount of ones it takes to build each number, because if we asked about the maximum amount of ones it would take, the answer would be infinity. Even to build the number 2, we could go 1 plus 1 times 1 times 1 times 1 times 1 as many times as we wanted. Let's say I was trying to build the number 7 with ones, plus signs, multiplications, and parentheses wherever I wanted them. Well, it wouldn't take 7 ones. I could do it with just 6 if I did it that way. Adding 2 there, 3 there, multiplying those, and then adding 1 more. And I considered 6, the amount of ones it took to make that number, as its cost, which I later learned could be known as its complexity. Here's a chart of the first 12 numbers, what I was thinking of as their cost, meaning the minimal amount of ones required to make them, and an example of making them that way. With the first 3 numbers, we want to just use addition. Multiplication wouldn't help. And with the number 4, we get to the interesting spot where we could use multiplication, multiplying 2 of 1 plus 1 with each other, or we could have just added all those ones, and either way we'd get the same result. Then at 6, we get to the interesting trait where the cost is smaller than the number. It's also the first time that we have a cost that was the same as the previous number. And following that, we get a 3 in a row, where 7, 8, and 9 all have a cost of 6. And 10 has a cost of 7, 11 has a cost of 8, but something interesting happens at 12. 12 is our first number that has a smaller cost than some previous number on the list. 12 we can build with just 7 ones, but there's no way to do that for 11. It's always going to take at least 8. Now, once we've built a number, we can use that construction to build other numbers. Like, since 6 only costs 5 ones, if I ever want to add 6 or multiply by 6 to make another number, I can use this construction to only pay 5 ones. And since every number larger than 5 has a cost smaller than itself, we're never going to want more than 5 ones in a row, all just added together. Anytime we would add more than 5 ones in a row without any multiplication in that mix, there would have been a cheaper way to do that part. For example, 7 is larger than 5, and 7 has a cost smaller than itself. It only takes 6 ones to build 7 in a construction. So if we ever want to make some number by multiplying something smaller by 7 or adding 7 to something smaller, we're not going to want to use 7 ones in a row. We're going to want to use that cheaper construction for 7 in that part of the mix. Similarly, if we had formulated our question by looking at ways of building numbers and we were allowed to use any whole numbers in our constructions, along with addition, multiplication, and parentheses wherever, but we considered the cost to be the sum of all of the whole numbers that we had used. Like here, we built the number 7, and we used a cost of 6 if we add these 3 components. Well, that question turns out to be basically the same as the how many ones it takes question, and in that formulation, we'd never want to use a whole number larger than 5 anywhere in our construction. When trying to figure out how many ones it took to make each different number, I also wondered the reverse question of if you were given a certain amount of ones, which numbers you could create from that. And that's a tricky question, but I did find a pattern in the largest number that you're able to make with a given amount of ones. Here are the largest numbers that you could make with 5 ones, 6 ones, 7 ones, and etc. And you might notice a pattern. They're all clumped in 3s and 2s multiplied together. And in fact, this pattern goes, there's some 3s and a single 2, then just 3s, then 3 and a pair of 2s, 3s and a single 2, just 3s, 3s and a pair of 2s, and this pattern repeats. All of the largest numbers you could make with a given amount of ones are in the form 2 to some power times 3 to some power. And if the amount of ones you have is 3even, or a multiple of 3, then this exponent will be 0, making that part 1, and it'll just be a power of 3. But if the number of ones you have is throd, or not 3even, then this exponent will be either a 1 or a 2. But what is it about 2s and 3s that are so efficient or important here? It turns out that the number 3 is so important here because it's the closest whole number to the number known as e. This number e, about 2.7, is an irrational number, like the number pi, meaning it has an infinite amount of non-repeating digits after its decimal point. And there are many ways to precisely define it. For example, if I look at 1 plus 1/2 to the power of 2, I get 2 1/4. If I look at 1 plus 1/3 to the power of 3, it's a little bigger. 1 plus 1/4 to the power of 4 is a little bigger still. But if I crank up this number in the denominator and exponent there, we don't continue rising forever. We end up reaching a limit of the number e. Now remember that our how many ones question is basically the same as if we allowed any whole numbers in the constructions, but then considered the cost to be the sum of all those whole numbers that we'd used. Well, what if we allowed more than just whole numbers? Like, if I was allowed to use 10 ones, or 10 being the sum of whatever whole numbers, if that's my formulation of the problem, then normally the largest number I'd be able to make would be 3 ones times another 3 ones times 2 ones times another 2 ones, which gives us 36. But if I was allowed to use my 10 a little differently, maybe I would go 2.5 4 times multiplied together, which does add up to 10 if I'm allowing more than just whole numbers. And this is bigger than 36. And in fact, whenever we're able to cut the pieces as close to the number e as possible, this is maximized. This is related to e's role with numeral systems and bases. We'll return to this in a future episode someday when we look at how efficient different bases are at expressing numbers, and look at how e maximizes certain traits about this. Now, since the number e is so efficient, when we're just using whole numbers, the closest whole numbers to it, 2 and 3, sort of get superpowers in terms of the largest numbers they can generate for a given cost, and especially 3, the one that's closest to 2.7 and etc. But although finding the maximum number was a simpler question, finding all the numbers that a given amount of ones could reach and then backtracking that to know the cost of each of those numbers was a trickier question. I began to visualize it sort of like a number line with different dots growing on it. Like if I was allowed 6 ones, these are the numbers I could reach. And with 7 ones, I would be able to reach all of those previous ones from the last web because I could have used the new one for a times 1 if I wanted. Or I could also reach these 2 new spots, and we now have a gap. Then with 8 ones, we could reach all of these numbers, such as spots that sort of crept up 1 from something in the last web by adding a +1, as well as other spots that are able to be reached with 8 ones, and other gaps. Now, I noticed that when trying to construct a prime number, it seemed like you always wanted to create the number 1 less than that and then add 1. So when I was researching this, I made the hypothesis that maybe every prime number has a complexity cost exactly 1 more than the number under that prime. But that hypothesis turned out to be false in a pretty surprising way. Sometimes you may think that a rule is true or that a pattern holds until you expand your view a bit larger. That hypothesis was wrong, but the smallest counterexample is larger than 350 million. This number is the smallest prime number that costs the same amount as the number beneath it, and that the quickest way to get to isn't to target the number right under it and then add 1, it's to target the number 6 beneath it and then add our construction for the number 6, which was 2 ones times 3 ones. Now, before I go into how I found out these facts about numbers that large, let me tell you about some other similar investigations I did on my own about how many ones it takes to make each number. Figuring out these webs and gaps was very interesting to me, and it wasn't the end of my investigations, because although using ones seems like something that makes sense, 1 is the unit, deciding that we were using addition and multiplication and parentheses only as what we allowed infinite of is a little arbitrary, so I also did experiment with other operations. Addition and multiplication aren't the only operations, so I did wonder what would happen if I incorporated subtraction as an option, and whether that would let you build any numbers with fewer ones. When I was first investigating this myself, I wondered if subtraction might never help us reach a number quicker. Like if I'm trying to reach some hard to get to number, like a prime number, I could use whatever cost is below it and then add one, or I could try and use a seemingly bigger cost to get to whatever's above it and still need to subtract one. But once I got to the number 23 in those investigations, I found that without subtraction, 23, the quickest path is to multiply 2 by 11, which is that whole mess, and then add 1, which is basically approaching it from 22. But then when I incorporated subtraction, I found that we can get there by approaching from 24 and then subtracting 1 in a quicker way, using less ones. This here cost me 11 ones, and this one only cost me 10 ones. And 23 isn't the only number with this property. These are the other smallest numbers that can be reached quicker if you allow subtraction. But what about division? Could there be any number that was somehow cheaper to get to if we included division along with addition, multiplication, and subtraction? We would have to pay for the cost of a number that was multiple times bigger, at least twice as big as our target, and then pay to divide back down to that. Well, I didn't find any examples of that myself, because I didn't check more than 50 million different numbers. It turns out that there are examples of numbers that incorporating division can get you to quicker. And this is the smallest example, more than 50 million, with the second smallest example being more than 250 million. Now let me explain how I went from my personal investigations to finding out these facts about these numbers in the millions. After calculating the costs of about 50 numbers, I ended up stopping doing these manual calculations because I'm not a computer programmer, so I was looking for some sort of pattern or maybe equation that would tell me what the next cost was, and I couldn't find one. It was pretty mysterious, whatever was going on. So I tried to look online to see if anyone else had calculated more numbers than me and what they had found. But it was really hard to search this online. When I searched something like how many ones make up each number, I got all sorts of different results that weren't related to what I was talking about. Luckily though, there's a website called the OEIS, which stands for Online Encyclopedia of Integer Sequences. Some people may overlook this website, the OEIS, because it has a very simple text-based design, but it's very useful. When it catalogs sequences, you can search them up multiple ways. Like, I could search Fibonacci sequence and see the notes about that, as well as many entries of it if I didn't want to calculate them myself. But I could also have a sequence that I didn't know the name of. Like, let's say I stumbled across the triangular numbers myself, wondering what's up with the sequence that goes 1, 1 plus 2 equals 3, 1 plus 2 plus 3 equals 6, and then 10 in a sort of triangular fashion. Well, if I searched some stretch of these on the OEIS, like 3, then 6, then 10, then the next would be 15, that would lead me to their entry about triangular numbers. On this website, which catalogs all sorts of different number sequences, as well as people's notes about those sequences, I searched a particular sequence, a string of numbers separated by commas, and what I searched was the costs I had gotten for the natural numbers so far. 1, 2, 3, 4, 5, 5, 6, 6, 6, 7, 8, 7, etc. And this led me to find that there was an entry for this sequence. The OEIS calls this the mahler-popkins integer complexity sequence, named after two people who originally wrote a paper looking at this topic. And what I was calling the cost of a number can be more formally known as its integer complexity. And although this isn't a topic that's taught much in school or that many mathematicians know about, now that I had gotten that phrase, I was able to search that online and find that there is a short Wikipedia article about it and a handful of papers written about it and some research done extending to sizes of numbers that I wouldn't have been able to manually calculate by hand myself. And there wasn't just a single entry related to this on the OEIS. There were other sequences listed here that I was able to find related to what was the cost or complexity of different numbers with different combinations of operations. In fact, I found an awesome table compiling many of these results by someone named Glenn Whitney, which showed many different sequences of numbers, not only the costs of them under different operations, but also things like what is the list of numbers that are cheaper to build if we include subtraction, or what is the list of numbers that are cheaper to build if we also include division. But even with all the cool information I was able to find out through this table and all these sequences, there were still a bunch of questions I had that I wasn't able to find any answers to. All the research I could find about how much different numbers costed when incorporating division was just looking at integers, like the name integer complexity would suggest. But I'm curious how much different non-integer numbers would cost as well. Like if we incorporated division, we could look at the cost of different fractions. Like let's say we were trying to build the fraction 5/6. At first you might think we have to build 5, which costs us 5 ones, and then divide by 6, which also costs us 5 ones for a total of 10. But we can get there with fewer ones. If I do 1 over 1 plus 1, which is 1/2, plus 1 over 1 plus 1 plus 1, which is 1/3, well, 1/2 plus 1/3 equals 5/6, and this one only cost me 7 ones. And I don't think that particular area of integer complexity has been explored much. So let me know if any of you have time to mess around and research this on your own. And if you find any other lists of fractions that are the ones that are cheaper to make by adding up different components as opposed to just making their numerators and denominators. And extending this to rational numbers isn't even the furthest we could theoretically take this. If we use things like logarithms and roots, we could see the cost of certain irrational numbers. We could even extend this to the complex plane if we incorporated the number I, perhaps treating that as like a 1 in the mix, where we can use them and count how many we've used in total for the cost of different complex numbers. Like what would be the cost of each Gaussian integer, which are the numbers that lie on the grid points of the complex plane, such as -3 plus I, or 5 minus 2I, or we could even combine that with the irrational numbers thing and look for the cost of numbers like 3/4 plus 2/7 I. Again, this sector of integer complexity has not been explored much, so let me know if you have any ideas of other ways this could be extended beyond just integers. I first found this concept, integer complexity, a few years ago, so why did I finally decide to make an episode about it now? Well, it's such a fundamental concept, despite being so underrated, that it showed up again in my life. Recently, I was trying to develop some card games, and through my mathematical research of which cards would do what in my games, which is a topic I'll save mostly for a future episode, different games I've been designing, I did rediscover the concept of integer complexity and found that I was looking at something very similar to that old how many ones made up each number question that I'd had a few years ago. And so I figured it's finally time for this concept that has popped up twice in my life, at least just the times I've noticed, to be made more publicly known. Now let's take a moment to look at some philosophical questions I came across when studying and investigating these things. Many people think that if you were testing one of your own hypotheses, a question you thought of yourself, that they kind of hope that they're the first person to be testing that question to that degree ever in history. Like if they looked it up, they wouldn't find any other results of anyone else doing the exact same tests that they are trying. They want to be the discoverer or inventor of sorts. But to me, there's more of a paradox at hand of whether it actually feels better or worse when you are researching a topic that is one of your own hypotheses and you can versus can't find any other results of people having studied it before. Now, some may see this as a lose-lose situation, because either you discover something that's already known and then you don't get to feel like you invented it, or you discover something that hasn't had any research published you can find about it, and then you're kind of stuck working on it on your own with no exterior help. But we could also see this as a win-win, where in one circumstance, you are the inventor or discoverer of this concept, and in the other circumstance, somebody else has already discovered it, but they've made some foundational groundwork of their own research that maybe you can build off, and maybe you can go further with this concept than you'd ever have been able to on your own. In this case, I was glad that I wasn't the first person to discover this concept, that it wasn't something that would be named after me, that there were a few mathematicians out there who had studied this integer complexity before, so that I could see these grandiose results about numbers bigger than I would have been able to research on my own. Perhaps some of you folks will enjoy playing around with some of these concepts yourself, whether it's the integer complexity question or the other related questions that we could come up with about how to combine certain simple units like 1 into other numbers, or in general, what numbers are composed of and which numbers can be built in different ways. Maybe you'll just have fun exploring this concept yourself, or maybe you could discover something cool mathematically. And that's probably enough for today's lesson. Thanks for joining me in combo class. I hope you learned some interesting things. Make sure you're also tuned into my bonus Demotro channel if you'd like to see my extra content like shorts and live streams and stuff. And check the video description for other cool links and information. And special thanks to all the people who help make this show possible, such as my Patreon supporters. Thank you all for joining me in combo class. I love you, and I'll catch you in the next one.